In this segment, we're going to talk about temperature, pressure, and specific volume. Just very quickly. So specific volume is the easiest. This is the volume divided by the mass to make it an intensive property. We mentioned that this was the inverse of density, so you may be more familiar with density, but it's just a matter of convenience of why we choose to work with density, or why we choose to work with specific volume rather than density in this class. Sometimes, like if you have a gas with a really low density, maybe it's more convenient to work with units of specific volume rather than a 0.0 something for your density. You have a whole number instead. Temperature. So we mentioned that we're going to be working with SI units and English units. We also mentioned that it is it's typically very common to have to convert to absolute temperature units, so Kelvin or degrees Rankine. And you might be wondering where the choice of 273.15 came from. And this corresponds to the triple point of water. So let's see. Here we go. So this is an experiment somebody ran to achieve the triple point of water, which is, actually, let me pause this real quick. Yeah, we'll come back and watch it again. But the triple point, it's defined by a temperature and a pressure, and it's specific for the substance that you have. So for water, it corresponds to a temperature of 273.1516 and a pressure of about 0.2 millipascals. So it's pretty low pressure there, pretty low temperature, well, 0 degrees Celsius. So at that temperature and pressure, water exists in 3 phases at the same time. Okay, so those phases exist in equilibrium, I guess is a better way of saying it. So you've got solid, liquid, and gas present at the same time. So with that in mind, let's look at our video here. All right, so you see like these green marbles. Don't worry about that too much. It's to provide sites of nucleation for the ice. But what you'll see is clearly you've got ice formation, and you're starting to see some bubbles forming, and now you see boiling. So you've got liquid turning into gas. That's your boiling reaction. And then you've got ice present as well. So you've got all 3 phases at once. So I just wanted to kind of give you a background about where that 273.15 came from. When you're doing calculations with temperature, you are most of the time you're going to have to convert. If you're dividing or multiplying by temperature, you're going to have to convert into absolute temperature units. The only difference is, or the only exception to that would be, is if you are doing calculations based on a temperature change. Because the temperature change in, say, degrees Celsius is exactly the same as the temperature change in Kelvin. So let's show why that is. Anytime in this class, anytime that you've got a delta something, a change in something, it's defined as what it is after minus what it is before. So the temperature that it is after this process would be T2, and the temperature that it is before is T1. So let's say that T1 is 0 degrees Celsius. So I've just picked that, just an arbitrary value, 0 degrees Celsius, and let's say T2 is 25 degrees Celsius. So the temperature change would be 25 minus 0, which would be 25 degrees Celsius. Well, let's say I wanted to stay on the safe side, and let's go ahead and convert it into Kelvin. So same thing, delta T would be what it is after minus what it is before, T2 minus T1. And if I converted my temperature into Kelvin, well, it looks like I still have a temperature difference of 25 Kelvin. So the number is exactly the same. So we see that a change in temperature in degrees Celsius and a change in temperature in Kelvin are exactly the same. But if you don't want to, if that kind of throws you off and you have to do calculations with temperature, just convert everything into Kelvin to be on the safe side. That's okay too. All right, pressure. So anytime that you evaluate system properties, you're going to need to evaluate them at the absolute or the system pressure. So the absolute or the system pressure, 2 ways of saying the same thing, it's equal to gauge pressure plus atmospheric pressure. All right, so atmospheric pressure is, well, it's at sea level, it's 1 atm, 101.325 kilopascals, or 14.7 psi. And you notice that we say that the atmospheric pressure, it's the absolute pressure of the atmosphere. So I just put PATM and didn't put absolute as well, but it's the absolute pressure of the atmosphere. And sometimes when something is given in absolute temperature units, you'll see an A at the end of like PSIA. So 14.7 psi and 14.7 psia, it just indicates that this is the atmosphere, or not the atmospheric pressure, but the absolute pressure of whatever you're talking about. So in this case, I'm talking about the atmosphere, the absolute pressure of the atmosphere. Gauge pressure. So here's a picture of somebody measuring their tire pressure with a gauge. Looks like they're measuring around about 23 psi. And if you wanted to be technically correct, you would write it as PSIG, indicating that it's gauge pressure. So PSIG, PSIA, it's a way of indicating which one of those things are you talking about. So the gauge pressure is the difference between the absolute or the system pressure and the atmospheric pressure. So just any of the pressures that you're going to be given in this class, it's going to be given as the system pressure, but I just want you to be aware going out and practice that there is a difference. And if you need to evaluate properties within a system, then you need to evaluate it at the system or the absolute pressure, not the gauge pressure. All right, thank you very much.